Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's show is the Juno mission sent out by NASA. And with me here in the studio to talk about this latest mission is our own Stephen Whitty. Stephen, welcome back to the show once again.
Yeah, it's good to be here. It's always good to be a guest on the show.
Well, we always like having you because you do bring such interesting topics. Now, Juno was just launched, so there's not a whole lot of data coming back so far. Maybe next year we can do a follow-up to it, but there have been other missions sent to Jupiter in the past, such as Pioneer, Voyager.
Yeah, Pioneer made a flyby of Jupiter in 1973, so this is a long time ago. I mean, it's quite a while ago.
And of course, we had Galileo about 20 years ago.
That's right, and Galileo was a mission to Jupiter. It didn't just do a flyby. It orbited around the equator. It looked at the moons. It measured temperatures on Io, so the volcanoes on Io, and it established that the rings of Jupiter does have rings. They're not as impressive as Saturn's, but it does have rings. And they are made up of dust and particles from the volcanoes of Io. So
sulfur, basically.
Basically sulfur and whatever else that Io decided to get rid of. Cassini also made a flyby of Jupiter, and we'll get to that in a little bit. Oh, well, here we are. So Cassini made a pass, if you will, under, that is, on seeing the south pole of Jupiter.
And that's our view here.
And that's our view here. So we've got the great red spot as seen from the sort of over the south pole, and up at the, what is that, maybe the 1030 sort of direction. And you can see the bands and the zones on Jupiter and the south pole itself.
And of course, this was shot as Cassini made its way to Saturn.
That's right, right. So Jupiter was used in some ways as a test of some of the instruments of Cassini at Jupiter before getting to Saturn. And
so now we're back with a mission dedicated to Jupiter in Juno, which is Jupiter's wife's name from Roman mythology.
That's right. And it is kind of funny that Juno comes from Jupiter's wife's name, whereas the other things that orbit Jupiter are Jupiter's mistresses and so on. So, maybe they could be a little jealous at this point.
Perhaps. So, all right. So we're going to talk about Juno and basically its arrival and some other interesting. So we do have on the arrival. So when the spacecraft gets to Jupiter, we do have the JPL team celebrating that it had gotten word that Juno had actually made it into orbit. So here they are; they're celebrating at the Jet Propulsion Laboratory, and they're all excited. And that's because Juno has spent 8 years getting. Juno has spent quite a few years. It was launched in, when was it launched? In 2011. So in 2016, it was 5 years. 5 years, yeah.
To make it to Jupiter. So they were quite excited that it had made it. And of course, before the launch and travel to Jupiter, Juno had, the mission had been under planning for several years. So
of course.
There was quite a bit before that, yeah.
So in the approach to Jupiter, do we have some of the first images taken by Juno?
We have the very first image on approach. So this is a picture with Jupiter and 3 of the moons, Io, which is the one with the volcanoes, Europa, and Ganymede, which is the largest. But also we have a couple of videos, and one of them we have the moons of Jupiter as Juno is approaching Jupiter, and Juno has these cameras, has a camera, the Juno Cam, and it takes a picture every so often, maybe every hour, and they made that into a movie for a week or two.
And this is the camera here?
So here is the camera here. So we've got the data recorder and then the camera itself. And then we have another camera, another image with the camera actually mounted to the spacecraft. So, you know, it's just sort of, it looks like it's just sort of tucked in underneath one of the wings. And Juno does have wings, which we'll get to. But these videos, I think we should introduce them. So,
all right.
So the first one is with Juno. It's approaching Jupiter, and Jupiter has this enormous magnetic field, and when you have anything moving in a magnetic field, you get an electric field as well. So Juno recorded data for hitting the magnetic field, but also hitting the electric field. And so, so this first video walks us through what that would sound like if you turned the data into sound that you could just hear.
All right, well, let's take a look at that right now. All right, so we get a feeling for what that would be like. The second video?
So the second video is with Juno Cam taking images every so often so that you see Jupiter with the moons orbiting around Jupiter.
Oh, all right. Well, this sounds equally interesting, so let's take a quick look at this one too. Well, now, these are the four largest moons of Jupiter, of course.
That's right, and they're named the Galilean moons since Galileo discovered them in his little tiny telescope. I mean, it was really tiny.
Yeah.
So any binoculars that you might have in the bottom of your closet would be better instruments than Galileo's original telescope. I think it's hysterical.
Yes, that's the way we've come with technology. Now, as part of this, I understand that Juno's going to be looking for some H2O.
Yeah, you know, you'd think on Mars it makes sense to look for water, but on Jupiter it also makes sense to look for water, and that's because oxygen is expected to be scarce on Jupiter, and so most of the oxygen in or on Jupiter would be expected to be bound to hydrogen. There's tons of hydrogen on Jupiter, and so you would then have water molecules.
Okay.
And
sure.
And so one of the things that what the Juno scientists will want to do is they will want to measure how much water there is on Jupiter, and if it's if it's a lot, that could mean that Jupiter formed further out from the sun. And where
water would tend to freeze and then fall into the big mass of Jupiter. You know, it could get scooped up easily, and even at the very beginning, it would start off icy and just grow more and more ice. So that's on the one side, and on the other side, if there is not very much water, then maybe the water that's there has primarily come from comets. Jupiter is known to have water that has it's heavy water in that you have not just hydrogen, but you have deuterium and tritium. You have more than one. You have a neutron added to the hydrogen atom, or you have two neutrons added to the hydrogen atom.
Stuff they call heavy water?
That's right. Yeah. So it's certainly heavier water. And it has quite a bit of that, and it isn't quite clear at this point why that might be.
But when we talk about water in this sense of being on Jupiter, we're talking about in the molecular state, certainly not a puddle of water.
No, yeah. Well, since there's probably no solid surface anywhere on Jupiter, there is probably a layer of water, and it could be enormous. That is, it could be more than, it's probably, I think, well more than the volume of the Earth. The entire volume of the Earth could be, you know, a big chunk of water.
Interesting.
They talk about, you know, as a joke, they talk about, oh, well, Saturn's density is so low that if you could put it into a bathtub, it would float, right? Well, Jupiter may have that bathtub big enough of water.
Float Saturn.
And of course, if Saturn got anywhere near Jupiter, their gravity would do all kinds of weird things. It wouldn't look at all like floating.
No, I don't think that's a place we want to go to. Speaking of going, we're about to the first part of this section of the show. If you have a question, send us an email, as we always suggest that you do. We like getting those, of course. And right after term of the month, we'll be back with more discussion about NASA's mission to Jupiter.
Thanks, Don. The term of the month for September 2016 is rocket. A rocket is a missile, a spacecraft, an aircraft, or any other kind of a vehicle, and it obtains thrust from a rocket engine. So a rocket engine creates thrust from propellant that is carried with the rocket before the rocket was launched. So the rocket doesn't thrust against something, it doesn't push against something, so it can be used in a vacuum. Here's Robert Goddard with his first rocket, and it is really pretty much the first modern rocket. He attached a supersonic nozzle to the combustion chamber, and he used liquid fuel, and he got the thing to fly. After 1945, this design, although much bigger, made manned spaceflight possible. So in 2016, in February, this is a map of the deep space missions. There were 15 deep space missions, and Juno is represented here, as are many other space missions, Cassini and so on. And that is term of the month for September 2016, rocket.
Thanks, Stephen. Welcome back to the program. Now, we were talking about NASA's Juno mission to Jupiter, and again with me is our own Stephen Whitty. So, we talked a bit about previous missions to Jupiter. We even talked about water at Jupiter. But what about the orbits that Juno is going to take around the king of the planets?
Yeah, so we have some images here. The first starts with Juno at Earth and making it to Jupiter. So we have the whole solar system, and so you start on the inner orbit. You know, the Earth is the third planet out, and it makes a kind of a convoluted double loop to get out to Jupiter. And then once it gets to Jupiter, there's an approach that Juno made to get to Jupiter.
Coming in from the left there?
So it's coming in from the left, and then it also comes in from the northern side, if you will.
Coming over the North Pole?
Kind of over the North Pole.
Yeah.
And it makes those orbits, and then each orbit takes a couple of weeks, and Jupiter in the meantime is spinning, so you get these orbits that stack up in this kind of interesting geometry. Juno is moving with respect to Jupiter on each orbit, so you get a different piece of mostly the northern hemisphere on each pass. So when you're finally done, you can piece together one big image, which we're showing now. So we have a fake image because Juno hasn't done it yet,
okay.
And we have the orbits kind of doing this weird spiral.
And so this is what it would look like if you could accumulate all those orbital paths.
That's right.
Okay.
So remember, Jupiter itself takes about 10 hours to rotate once. So even though Juno is going quite fast when it's moving by Jupiter, because it moves fast where it's near Jupiter, it moves much slower when it's farther out from Jupiter. So it spends most of its time farther away from Jupiter when it's doing the close pass, and it can do images with JunoCam, and it can take measurements for the magnetics and so on.
So these will all be elliptical type orbits.
Yeah, yeah, and you get that characteristic serpentine sort of curvy orbit there, because you have Jupiter's rotation with the probably the north to south or south to north pass at Jupiter.
So it will go into its orbit once it arrives, and then start its data collecting?
That's right. That's right. So in just the first pass, they had planned to make to get some pictures with JunoCam, and at which we've already displayed.
Okay.
And on the subsequent passes, they will be making JunoCam. They will get JunoCam partial pictures of Jupiter, which will be spliced together in due course. So we won't actually see that sort of data. Now
that'll take a while as we accumulate those orbits and getting each slice of Jupiter.
That's right, and there'll be lots of patching. And in the meantime, of course, the clouds of Jupiter aren't static. They actually move with respect to each other and so on. So there's actually quite a bit of patching that has to happen. There's this other science that we mentioned, looking for the water, and we do that magnetically and electrically and so on. And the science papers that will come out of that, they will take some time, probably after the mission is over, before we see that, maybe 6 months or even a year after the last of the data has come from Jupiter to the Earth.
So there'll be this data collecting, and then there'll be the stream that is sent back to Earth, much like we did with New Horizons and Pluto, right?
That's right. That's right. And it's the same deep space network. So there are big radio dishes on Earth. They're in the U.S. and in Australia and in Europe, in Spain. I believe it's in Spain. Sure. And these 3 radio stations guarantee that at least one of them should be pointed in the right direction at whenever the data is being sent. Of course, Juno has the capability to store some of its data and then send it. So, for example, when we're on the opposite side of the Sun from Jupiter, which should be for at least a couple weeks, that the spacecraft can store the data and then transmit it when it's clear of the Sun.
Okay.
So there are considerations like that. And
well, that's true, yeah, because you wouldn't be able to send it through the Sun, but that would be interesting.
Yeah, yeah. So we've actually gotten quite good at sending data from a spacecraft at Mars when it's quite near the Sun from on the straight line path to the Earth. So we're getting better at that. You can actually lose less, I suppose. Here we have an image of, it's really a drawing of what Juno looks like. We've got solar panels on 3 arms, 3 really quite large arms. You can see the picture of a human for scale. So Juno is quite large. It has these solar panels. It does not have a nuclear reactor, which has been traditionally the way that spacecraft have been designed to go out to Jupiter. There isn't anywhere near as much sun at Jupiter as at the Earth.
Or Mars, for that matter. Yeah.
Or even Mars,
Yeah.
right. So you have to have quite large solar panels to make that work at all. And then on top of that, the Juno spacecraft, the body of the spacecraft is that hexagon in the middle with the circle in it. The spacecraft rotates, and so these big solar panels are rotating around in a circle. And so we call that spin stabilization. So the Juno spacecraft, you get it spun up, and you use little thrusters to make that happen. And once it's spun up, the spacecraft with the solar cells are well balanced, so that the spacecraft doesn't wobble. It basically stays pointed where it was. That's right. So,
keep the images.
so this turns out to be a very inexpensive and reliable way of stabilizing the attitude of the spacecraft.
You don't have to pack all that fuel to keep.
That's right. That's right. You do have to have some thrusters, but you don't have to have anywhere near it. You're not expecting to use that much fuel to do that. And that turns out, so it turns out to be a cheaper way of getting your stabilization. It's also very good stabilization. One of the features of it is that it doesn't depend on the computer for staying put. If the computer crashes for 2 days and then wakes up, chances are it's going to be pointing very accurately where it was pointed before.
And how long are we looking to have Juno at Jupiter? Have you given us any indication?
So it's only doing 57, 58 orbits. At least that was the mission that they had prescribed.
The primary mission? Yeah.
The primary mission. I don't know if there is even a follow-on mission for Juno planned, but 2 weeks times 50, right? You figure 1 week times 50 is a year, so it'll be a 2-year mission.
All right. So we've got a real good chance coming up in the next year or so to really have some good data collection and come back and give our viewers a really good update on what Juno is doing at Jupiter.
That's right.
Well, I want to thank Stephen for being with us again and giving us this preliminary report on the Juno mission. We always encourage you to visit the club website, the Ford Amateur Astronomy Club website, the address of which we always put down there at the bottom of your screen. And before we go to What's Up, I do want to mention, if you're viewing this show in September before the 9th or the 10th, keep in mind that we're having Astronomy at the Beach at Kensington Metro Park. You can go to the Metro Park website or just Google Astronomy at the Beach. You can get all the details. It's a Friday and Saturday night. Come on out, and the main speaker will be talking about next year's solar eclipse. So coming up next is Stephen with What's Up in the Night Sky.
What's up in the night sky for September 2016? The autumn equinox is on September 22nd. That means that the month is getting shorter, heading toward the winter solstice, and as the days are getting shorter, the fastest. So at the beginning of the month, the sun rises at 7 a.m., sets at 8 p.m. At the end of the month, it rises at 7:30 a.m. and sets at 7:15 p.m., at least here in Michigan. Southern Hemisphere people are getting longer days. The moons start out with, on September 1st, a new moon, and we'll get back to that. On the 9th, we have the first quarter. On the 16th, we have the full moon. And on the 23rd, we have the third quarter moon. But on the 30th, we once again have a new moon. So there is no term for the second new moon in a month. If it were the full moon, that would be different. On the first of the month here, we have Mercury. We have the moon also. The sun is just to the right and just below the screen here. So I'm sorry. Yeah, right, just below the screen. So we have the moon, we have Mercury, we have Jupiter and Venus. Mercury is going to be very difficult to see. It was difficult to see at the end of August. On the 12th of September, we have inferior conjunction, which is where Mercury passes directly in front of the sun. It's going to be totally impossible at that point. At the end of the month, here in the east, we have Mercury rising before the sun, and since we had the superior conjunction, we had the widest western elongation on the 28th of the month, Mercury is actually fairly easy to see on the 28th or here on the 30th of the month. Venus and, Mars, Saturn, and here we have Pluto are visible, and we're just showing this on the 15th of the month. Pretty much any day will do. So we're talking about 9 p.m. Saturn and Mars are fairly close together. Pluto is going to be very difficult to see, and I've just shown it to give you an idea. So Saturn and Mars in Scorpius. See the Scorpion below the two planets, and then Pluto is in Sagittarius. And then finally we have Neptune and Uranus. So here we have Neptune to the right there, Uranus to the left. Neptune is in Aquarius, the water bearer, so I guess the pot is below pouring out the bucket. He is pouring out the water at the bottom of Neptune, at the bottom of the constellation that Neptune is in. And Uranus is in Pisces, the fish. So, but back to Neptune, if you really want to see a Neptune, you're going to need a better star chart than this one. You'll need to zoom in. This is the same shot, just zoomed in. You see the moon is much bigger. That's just for scale. We still have a fairly bright star fairly near Neptune, and that it's been near for quite a while. But you see all of these little dots. You're going to need a star chart at least this detailed in order to see Neptune. But you can see Neptune in a decent pair of binoculars if you know what to look for. It's weird. It's kind of a turquoise. It's a weird color for a star. There are basically no green stars for technical reasons. And that's what's up in the night sky for September 2016. Keep looking up. It's the greatest free show over your head every single night.
Amazon. A year and a half ago. I kept saying, I gotta get it eventually. That's the point I do it. Get what? We've been struggling with your order for a year and a half. Our vendors have failed to come up with this quote. We are sorry to disappoint you.